Yes, sir.
Yeah, good afternoon, everyone. So I've shared this notebook with all of you. Um, we've created this notebook in such a way that it also weaves into some of the other optimization techniques, especially based on subset selection that I'll cover during the second half of the course, maybe little latter part of the second half of the course. So we have this library called Spear. Can you see this tutorial? Screen shared. I'll make it full screen. Okay.
Yes, sir. I think so.
So um, it's making use of Spear, which is semi-supervised data programming. That's what Spear stands for. And there's associated paper and documentation here, as you can see. Um, so the data set is loaded through that. Though our methods that we write are kind of from scratch, we don't, the Spear itself has lots of optimization libraries that it uses. Whereas here we are trying to write the optimization algorithms from scratch. So data loaders, etc., we are reusing from there. So um, the SMS Spam data set specifically is on what I illustrated. It's a binary classification data set. You are given SMS and you want to detect if it's a spam or a ham, which is a non-spam. So featureization, etc., are built here. And now we're going to use logistic laws largely. And this is our very basic implementation of gradient descent. Okay. We exit when some optimization condition, and we'll talk a little bit about that. Right, what could be convergence criteria once we finish our convergence analysis. But until some convergence condition is satisfied, or if the number of function evaluations is exceeding the max number of function evaluations, okay, which has been set here. Just trying to find out where I have said it. Okay, actually, sorry, it's passed as an argument here. Max evals is passed as an argument. So moment the function evaluations exceeds that, then you break. Right? Either of these two conditions, uh, with the optimization condition being given precedence. Okay, and here's a simple, run of gradient descent. So you can see the function value, and this is the function value, and now what we're trying to see is the optimization condition based on which we would the opt condition, which is supposed to be less than say 0.001, and we are just checking. Okay, what is optimization condition? It's basically looking at some kind of gradient. We'll look at this, right? Something to do with the gradient here, G. Okay, so you keep on inspecting it, and the moment it becomes very small, you plan to exit, or right, or the function evaluations exceed some threshold. Okay, so here we have said actually function evaluations is 250. Yeah, so it has exceeded. Moment it has reached 250, it has quitted. Okay. Now you will see a couple other implementations, gradient descent with Arduino conditions. I'll talk a little bit about that today. Different kinds of. I have some extra slides though, where I refer to these. So yeah, a couple of other algorithms that we will talk about are implemented here. Okay, but this is the simplest of that. What we have discussed is illustrated here in this notebook. Um, and let's go back and understand why this gradient descent would converge. We talked about convexity being useful, but at the same time, Lipschitz continuity, which is more or less kind of guaranteed if you're looking at convex functions in certain bounded regions, right? So more or less Lipschitz continuity holds, and then Lipschitz smoothness holds for a subset of such functions. Okay, we'll discuss a bit more of that today. Can we switch to the slides? Anyone wants to ask anything on this? Okay, so there's more in the notebook as we progress on our understanding of the convergence. So we'll continue our discussion on Lipschitz continuity, smoothness, and convergence of optimization algorithms. Okay. Yeah. So we had left ourselves with the gradient descent discussion and its convergence. We specifically were interested in what happens if it's Lipschitz continuous with parameter b along with convexity. Okay, so this is a recap, and I left you as homework to complete the analysis. So I'll recap what we had covered as part of the analysis. First part was just algebraic manipulation. Okay, so 2v transpose w could be written as norm v square plus non w square minus norm of v minus w whole square, and we just substituted for v as gt and then as w as xt minus x star. With that substitution, we got certain expansion by applying this algebraic equivalence. Then what we did was we took this equation 1 obtained as a result of the algebraic expansion and summed it over t iterations. T equals small 1 to t minus 1. So small t ranging from 1 to t minus 1. So we finished this part. I'm assuming you don't have any questions on this. We were wondering then what can we do? How can we simplify? So there were some important inequalities that come to a rescue. One being that at the teeth epoch you're probably not yet converged to X star. That's what you're continuing. So if you have not converged, then what happens to the right hand side in conjunction with convexity? So there are two things we are using here: invoking convexity with x equals xt and y equals x star. So that's one. This is use of convexity, and the other is that the teeth iterate has not yet converged to x star. I mean, the fact that there is no more need to update, there's a non-zero gradient, right? I mean, had x star been achieved, you would have at least expected the gradient at the previous iterate to be 0. But there's still some scope for update, right? A gradient at xt to be 0. There's still some scope for update. So what do we do next? You basically now, so there's a problem with the numbering here. So let's just write down the numbering properly here. This is combining 2 with 3. Combining 2 with 3. Okay. What's happening? If we have gotten rid of our blue term here, xt minus x star, and we have also applied transitivity of the inequality. So f of xt minus f of x star is less than equal to gt transpose xt minus x star, and this term gt transpose xt minus x star is also sitting here in this inequality summed over the indices t. So now therefore you can invoke on the left hand side the sum. That's exactly what has happened. We invoked the summation on the left hand side expression. Okay. The right hand side pretty much remains the same, except that we have dropped the term in blue, which is anyways greater than 0. So what have we done? We have said that by virtue of this, the part in blue is greater than 0. So this is therefore this entire expression here is greater than the expression here because xt minus x star square is greater than 0. And strictly greater than. Okay, so far so good. What do you do next? Any thoughts?
So I had a question about equation 2. So why
Yes.
isn't the inequality reversed? The gradient is upper bounded. The gradient should be upper bounded, right? Instead of gradient upper bounding the LHS.
Okay, so just read this a bit carefully. What is the original inequality? We are talking about GT, right? So we know that f of x star. Okay, let me write this. F of x star as per convexity, right? So look at this convex function. If you have a, a linear lower bound at this point xt, sorry, I should have, yeah, I'll do it here. So this is xt, and this is your point x star, the lower point. So we know that f of x star is lower bounded by f of xt plus gt transpose xt. Actually, it should be x star minus xt. F of y is greater than equal to f of x plus g transpose y minus x, right? So x star minus x t. Okay, so now what have I done? I have taken f of x t and f of x star on one side, which is less than equal to. So I have moved um, this expression to the LHS, right? F of x t minus f of x star. That's what happened here. And when I move the gt x star minus x t to the RHS, the sign gets flipped, right? So gt xt minus x star you got. So that's greater than. So it's the same thing. Is it clear?
Yes, sir.
Okay, so the mistake you might make is take an xt minus x star here. So note that is x star minus xt. That's when this will serve as a linear approximation. Linear approximation, which is also a lower bound for a convex function.
Okay.
Yeah, thanks. Um, Anything else you want to ask? Clarify?
So equation 3 is x1 minus x star square, right?
Equation 3 is
In the right hand side,
um,
second term, that is x1.
yeah. So I sometimes indices yeah, let's make it x1. Thanks for pointing out. In the slides I would probably used 0 index and I forgot to change the indices consistently everywhere, but mostly should be consistent. Thanks for pointing it out. Any other question? Okay, so so far you are good, right? Um, okay. So then the next thing yeah, after invoking convexity, um, what did we do next? This is based on convexity. What did we do next? I kind of left it at left it as some little bit of food for thought as homework. We invoked something to deal with the GT norm square, right? We want to make sure that any known property can be which is somewhat natural and organic to expect can be applied. So the next natural property we would be interested in is Lipschitz continuity. So you have to look for properties, well known properties, and therefore one thing you're doing in this course through some of these example analysis is that you're getting hold of the tools, getting hold of definitions that might be handy. So Lipschitz continuity can give us some bound gradient norm. Now the question is, of course, we can give us some upper bound. We use that as it is, or do we do some manipulation is the question. Anyone has attempted hereafter? Anyone? Okay, if you haven't, let's move on. So we just now recalling what we have in the previous slide, the final result. Okay, now we want to do something with this red part. Okay, I colored it as pink, but let me just use red color to be consistent. Okay, so we are going to do something with this this component in the next slide. Just want to be consistent with colors here. Okay, so this part, the norm GT square, as I said, if we can make use of the Lipschitz continuity property, what happens? So this norm GT square, that's the right hand side, right? Norm GT square is less than B square. Now, how many times am I summing? Well, for t equals 1 to t minus 1. The B, of course, has no index into the t, right? So B is independent of t. So you'll have t minus 1 B square on the right hand side as an upper bound. Okay. So you'll have gamma by 2 t minus 1 B square plus the one more property we are going to use. Okay, so we are saying that no matter what you do, your iterates wouldn't have been, infinitely far away from your original, from the optimal point, right? So can we make use of some property like this? And we just draw the circle here. So what are we doing? We're saying that your iterates cannot be x star, which is your sought after point. The any x may not be very far away, and we can ensure that x1 at least is not has limited distance from x star. So x1 minus x star is less than or equal to r. Okay, so that can be applied to this term here, x1 minus x star square less than r square. That gives you r square by 2 gamma on the right hand side. So this extreme right expression, gamma by 2 tb square plus r square by 2 gamma. Now what do we do with that? Okay, this is a trick number. I've added some tricks so far, right? So we had trick number 1, which was algebraic manipulation. Trick number 2 was telescopic summing, right? This is trick. I probably have used many more tricks, like I will give them numbers. The trick 3 is what do you do about gamma? What we can do is you can see how small can the upper bound become, right? Minimize or determine the minimum value of the upper bound. Which you can, right? If it's upper bounded, then how tight it can become. You can likewise, sometimes you'll do maximum value of a lower bound. Add this kitty of tricks. Okay, so what have we done here? We are saying the extreme right expression. We will apply this trick 3, this expression. And how is our trick helpful? So instead of having an upper bound in terms of gamma, we are trying to find, well, is there an upper bound I can write independent of gamma? Okay, and that becomes possible by setting gamma to r divided by b square root t. So this I would leave it as homework. I mean, this is a very simple homework. It's a one-dimensional problem, right? So you basically are trying to minimize this expression with respect to gamma, and that yields gamma equals r upon b square root t. Now, if you can substitute the expression for gamma, the minimizer, what do you get? Can you please work it out? Let's work it out. Let's see if there's some insight you get. Please let me know what you will get when you substitute.
RB square root t.
You get what? R
into b into square root t.
R into b to square root t. Okay. Okay, so r into b into square root t. That's exactly what you had anticipated. Okay, so see, there are other ways you can look for actual gamma instantiations, right? What we did is just set gamma to r square b square root t. Okay, and we are doing that consistently everywhere, not just right hand side, left hand side also we have done that. Okay, so right, so recall that we have this. So this is what. By the way, why are we? I mean, a very important question to ask, which I didn't. Why? How are we boldly minimizing with respect to gamma when the left hand side here had a gamma? Anyone wants to answer that? I mean, really appreciate if you get the right answer. So here on the left hand side, you have a gamma. Right hand side, you have a gamma. Now we are saying determine the minimum value of an upper bound. But what if the left hand side that you're upper bounding had a gamma? Anyone?
Is it because the inequality holds is true for all gamma, therefore we can still continue with minimizing with respect to gamma?
Okay. So see, if this were the only inequality, thanks for the good attempt. As in left hand side, you're right. If the left hand side did not involve gamma, exactly your logic applies, right? So let me write this down more generally. So let's say I have an expression E1, okay, which is less than equal to E2 gamma. And E1, if it was independent of gamma, then you will say that E1 is less than equal to min over gamma of E2 gamma, right? That's what you're saying. Is that correct? In fact, the two are equivalent. Saying that E1 is less than equal to E2 gamma is the same as saying that E1 is less than equal to the min of all of those. Is that that's what you meant? Sorry, I didn't know who suggested that.
Yes, sir.
Yes. What now? My question to you is, what is E1 and what is E2? Let's give names here. What is E1 and what is E2? So can I assume that this is E1, this is E2, sorry. This is E2 gamma. Right, this is E2 gamma. If this is E2 gamma, what is E1 gamma? E1, which is independent of gamma, sorry. Anyone? Is there some noise from here? Hello? Neil Kamal, are you speaking something? Okay. Neil Kamal? Sorry, I have to mute you.
Sorry, sir. I guess it was unmuted. Yeah.
You wanted to suggest an answer? What is E1? Anyone would like to attempt this? What is E1 here? E1 here is this expression, okay? So we are not really talking about the intermediate expression which we upper bounded. We are talking about the original expression that we are upper bounding, which is this expression. Okay, so this is E1, which is independent of gamma. Okay, and otherwise we won't dare to do this. Okay, so this is important. Is this clear to everyone? So I'm again making this point. This E1 is independent of gamma. And therefore you can minimize the right hand side with respect to gamma. Hope this is clear. If you have questions, let me know. Okay, so what we are not interested in the intermediate. This part which I have invoked, this is really intermediate. We don't have to really minimize this with respect to gamma. Just minimizing the final upper bound and the original expression that we are upper bounding. That's all. Okay. That's what happens. So again, I want to remind you, we are dealing with E1 here, which is independent of gamma. Okay, let me write that even again here. E1, which is independent of gamma. And what you have on the right hand side is the E2, which is not just E2. Now we are going to go from E2 to min over E2. This is E2 gamma. And then what I have here is min over gamma of E2 gamma. So kind of repeating here so that there's absolutely no scope for confusion. So all this should be very interesting. It's giving you really powerful tools. So now we have said that f of xt minus f of x star summed over all values of t average, right? I mean, or rather 1 upon t, right? It's less than equal to rb into divided by square root t. There's a little bit more we can do, right? Instead of just doing a summation, leaving it at this point, what we want to do is we want to say this expression, which involves the argument. I think the argument got missing here. I'll correct that. It is x star x hat, which is argmin over I of f of xi. Right? This is a final iterate, the final smallest point, right? Because the whole idea is as we are proceeding, the function value is decreasing, and we are expecting the function value to decrease across the iterates. So that's a reasonable assumption to make. Otherwise, why would you do gradient descent? So therefore, I'm saying that let me write that. You're saying here, this is say f, but now f is with respect to xt. And what we have is t as an index here. Okay. So what we expect is that the function value decreases. Maybe there's decreases high, rate is high, and then it's. And so we are saying, well, at some point you decided to stop. The point at which you decided to stop is your xt or x hat. And this is x hat. So now what we can do is consider a minimization, or rather the lower bound for this, right? As since any xt, right? So there are lots of xt's. The previous xt's are further away. There's some xt here, right? And the corresponding f values would have been closer, far further away from f of x star than at x hat, right? Maybe x star, or I mean the function value at x star would have been, let's say, let's actually draw a hypothetical line. I don't know where that x star is. That x star I don't have access to. Okay, but what I know is that okay, it's probably here, right? F of x star may be here. So while f of x star is here, what this plot is showing as the evolution of or reduction of the function across epochs t. So if f of x is decreasing, f of x star is like somewhere maybe below f of x hat. But we would certainly expect f of x hat to be closer to f of x star than any of the other iterates. That's the reason you're doing gradient descent at all. Otherwise, why would you be wasting your time descending? You would have stopped earlier. Let's just give this a name. This is f of x hat. So given this, can I do some more manipulation? Yes, you can. What do you do next? Anyone?
I had a question here.
Yes, please go ahead.
Will x hat always be the last? No. Why? If our function is convex, so our point will move towards the point of minimum. So why wouldn't the last iterate be the argument?
It's possible that it turns out to be x star, but maybe your resource constraint, maybe you don't want to run to total convergence. Maybe your convergence criterion is based on validation set and not training set, right? Think of machine learning. We're not just thinking about optimization. So I want to
saying
stop.
we missed the point.
We didn't miss. We didn't necessarily go till that point, right? In machine learning, we may stop early on descending on the training set because we want to not overfit on on the training set. We want to do well on validation set. Okay, so you recap this from machine learning. So recap from machine learning that often the iterations are stopped based on validation set. That is when validation accuracy starts dropping. And here the optimization is with respect to training set. So we may have early stopping for avoiding overfitting / to generalize. Is this clear?
Yes.
Right. So from machine learning, the multiple reasons why you may not go to X star. This is one reason. It's possible that because of numerical precision. Another reason. Okay. So let me list down reasons. Right. This is certainly one reason. Another reason is that numerical errors. Okay. Let me just go give it. Numerical precision can sometimes be a deterrent to get X hat equal to X star. Okay, so these are this is another reason. So the equality I'm talking about here is f of X hat becoming exactly equal to X star. Is this clear? That's also a reason. That's a very good question you asked.
Sir, so this value of gamma that we have obtained, does this guarantee that we will never overshoot X star?
This particular gamma, see, there are two parts to your question. What should be the value of gamma for which you get convergence? Here we are saying that so no matter what gamma you use, okay, this is saying no matter what gamma you use, if this upper bound holds under Lipschitz continuity, this will always hold, no matter what gamma you use. I mean, obviously gamma is non-zero, otherwise you're not making any progress. Is that clear? So that's one aspect. That's why I'm saying minimization over all possible gammas. Basically, this inequality holds for any gamma. The key is this inequality is holding for any gamma. Is that point, first part to the answer clear?
Yes, sir.
Okay, so I'll have to say holds for any gamma, but we should just ensure that gamma is greater than 0, otherwise we're making no progress at all. That's one. But you have another valid question. What should be the value of gamma? For some other criteria, we'll find that there's an existence of a gamma for which you can show certain convergence properties or rate of convergence. So gamma in general, gamma values or choice of gamma values can make a big difference to convergence, right? So that's why this step size choice is itself a big topic of discussion. I'll be posting some extra slides on how step size can be chosen. Okay, so there are multiple points we're making here. In general, however, step size choice or choice of step size can be critical, important for algorithms, for and even analysis. Any other question? Okay. Great. These are very good questions. So let me continue where on this part of min over I of f of xi, which is f of x hat, or the argmin is x hat. What can I say if I try to apply this part here? What will happen? Can you suggest what would happen? Can I say that this sum over t, right? I mean, this is there's of course a t. I mean, there's a t minus 1 and divided by t, but we can consider it to be t by t. Okay. So can I say that this, right? This is like if I take a 1 upon t, and I say this is nothing but f of x hat, which is less than or equal to 1 upon t summation t equals 1 to t minus 1 of f of x hat minus f of x star. Can I say this holds? And my claim is because as you see in this image, as we progress, the function values can only get closer to x hat. They cannot get further away. This is the by design, right? The algorithm itself is meant to progress when function values are reducing. You're minimizing. Irrespective of whether you reach fx hat x star or not, you would have made progress. That's the whole idea. Okay.
The second inequality is okay. How do you get the first one?
So if you, I think you're saying how do I get t? Yeah, that's a good question. Yeah, let me just put this as approximately equal to. You're right. There'll be one additional. You'll have t minus 1 here. I think we can add a dummy term here. I have to maybe think a little bit more. At the least, we can write this as, if you want, you can just write it as t minus 1 divided by t. Let's just keep it at that, right? So this is t minus 1 divided by t.
Excuse me, sir.
Yes.
For the leftmost expression, shouldn't it be f of x hat minus f of x star? We wrote just f of x hat. That's why.
Sorry. Yeah.
Yeah, that's the point.
Okay. Oh, you mean that? Okay. And about the t minus, yeah, the t part is also something we can manage. This is additional scalar, but that's not very important. It's just one small addition. But this holds exactly. What I've written is correct. Now show that, oh, there's a problem here again. There's an argument, somehow it's gone missing in the compilation. So x hat again, as I said, is argument. Let me copy that from the previous slide. Okay, so this is x hat equals argument over I of f of xi. So you can show that modulo that t minus 1 term, right? It's pretty much this. Okay, so this can be shown. That f of x hat minus f of x star is less than equal to, the absolute value is less than equal to rb divided by square root t. So then let me ask one question. How do we proceed from here? One way which you could try and answer is suppose we want to find t such that, okay, find a t such that this expression on the left f of x hat minus f of x star, its absolute value. This is close enough, which means it's less than epsilon. I have no idea what is f of x star. Okay, so please note that I'm in total darkness about f of x star. We don't have access to. But all I'm saying is, in intention, I want to be very close to f of x star, close than epsilon. What is the implication? So let me ask you a question. Is there some sufficient condition on t that will get me this expression?
So we can have RB by root T less than epsilon, then it will hold.
Excellent, excellent, right? And this help derive a sufficient, I mean necessary, it may be sufficient condition. Okay, T must be something, at least something. And what was suggested is exactly the answer. A very straightforward answer. Right? What are we doing here? Yes, the answer is yes. First flip numerator and denominator. And then what we do? And then square, right? Is that the answer? You have to square as well?
Yes.
Okay, so let's write that expression. We'll have just flip numerator and denominator. I mean, let's say I want this to be less than equal to epsilon. This should be less than epsilon. But I know that f of x hat minus f of x star is less than equal to RB by square root T. So sufficient condition. What's a sufficient condition that f of x hat minus f of x star in absolute value is less than epsilon? A sufficient condition is that epsilon is less than equal to RB by square root T. It's not necessary, it's not that sufficient. Okay, which is amounting to saying that, sorry, did I make a mistake? No, it has to be other way, right? It has to be other way, correct?
Epsilon greater than R2 by root.
Yeah. The other way. This is a sufficient condition. So as long as this RB by square root T is less than or equal to epsilon, you'll know that f of x hat minus f of x star is less than equal, strictly less than epsilon. Well, you can, yeah, this can actually, yeah, you can make a strict inequality also, but yeah, it's just okay. So the sufficient condition will then be that T, just flipping things, right? R square B square divided by epsilon square is less than equal to T. That is, T is at least R square B square by epsilon square. Okay. So this is the idea. It suffices to have this, which implies that T is greater than equal to R square B square by epsilon square. Wow. So this we have really got from, long way basically from gradient descent to guarantee on when you would be close enough to an unknown f of x star. This must be very satisfying overall. And we can also try and summarize this by saying, okay, if the T is of this form, I mean, in an inequality sense, then it should immediately remind you that this is related to order, right? That for all epsilon greater than equal to some epsilon naught, T is greater than equal to some function, right? So that function is what? It is 1 upon epsilon square. That's the order term. So big O. Okay, so this is the big O term in algorithms. Anyone wants me to explain what is this big O? I'm assuming that silence means you're all fine. Okay. So this is t. T is order of 1 upon epsilon square. Okay, so
Excuse me, sir. Could
yeah.
you just give a brief overview of the big O notation? It will be helpful.
Right. So it's basically a notation which is talking about the limiting behavior, right? It's like what happens when the argument here, which is epsilon square, as it becomes larger and larger, how does it tend to be? Okay. So big O is about the limiting behavior of the function. What is that function? It's a lower bound, of course, for epsilon.
Sir, for lower bound we use big omega, right? Like, isn't big O for the upper bound?
Yeah. So this big O is in fact the upper bound right here. Oh, you're sorry. You're talking about yeah. You're right. You're right. This is the I was referring to the previous inequality, so we should just use omega here. Thanks for the correction. Omega. Yeah. So we're basically talking about a lower bound for t, not upper bound. Yeah. Let me use omega. Yeah. It's called big omega. Okay. So again, big omega is also limiting behavior, but in what sense? Yes. What is the difference between big omega and big O?
One lower bound, one upper bound.
Yeah. So here we are talking about a lower bound, right? The lower bound sense. Okay. So limiting lower bound behavior. Yeah, and what we are saying here is that you can basically characterize that different functions with the same growth rate. You can characterize using the same big O, big omega notation. Basically, it's an asymptotic bound. Okay. Big O, for example, is saying that if a function is f1 is O f2, right? As x tends to as the argument tends to infinity, then basically you're saying that the function absolute value of f1 is less than equal to some constant m times the function f2 applied to the same argument. Okay. In this case, we are talking about a lower bound. Absolute value of f1 is greater than equal to the some constant m or n times the function f2 applied to the same argument. Okay. So you can read up a bit more on this order of convergence in terms of algorithms. But let's try and understand what this means in with some examples. Okay. So the idea is we have given Lipschitz continuity and convexity. We have gradient descent with step size gamma equals say this is a existential gamma, but we showed that this inequality holds in general, right? So if you use this gamma, then that's a minimum. I mean this gamma or any other gamma. Gamma greater than 0. So H is a solution X hat, which gives you this upper bound epsilon and R square B square by epsilon square iteration. But let's understand this in terms of some example numbers and also analyze this a bit more. The advantage is that it goes to 0 as t becomes very large. Okay, so just go back to the previous slide. So as t becomes very large, you're basically having bound going to 0. That's an advantage. And it's independent of the dimensionality of x. Well, except for the fact that the gradient computation will depend on the dimensionality of x, right? So modulo that. But here, when we say we are talking about bounding, convergence, etc., we are assuming that each gradient computation is a unit step. So it's important to explain what is a unit. The unit of each step / analysis gradient, which is a single gradient computation. So we are not really accounting for the time required to compute the gradient. So modulo that, yes, is independent of the dimensionality of x. Okay. Any questions? Any other observations you want to make?
So the R is still dependent on X star. While you said that we are in complete dark about the value of X star, but still we are.
That's a good question. Yeah. So R is indeed based on how far the initial iterate. All we are saying is we are bounded by. I mean the points are not too far away. See, the issue is that there's not so much you can do about the choice of x1, right? I mean, we don't know x star. Sorry, let me just copy that image itself. Let's discuss this a bit more. Let's discuss this here. The R is an issue for us, but it's going to be issue for any initialization, right? Because it's for x1. So it's kind of independent of what algorithm you have. Right? Instead of gradient descent, you used Newton or subgradient descent. You would have the same x1. Right? So we are saying that that's based on how well the initial iterate was engineered. So it has little less to do with the algorithm. I mean, it's another matter altogether that the convergence for that algorithm is dependent on how far x1 is, right? Yeah, this particular analysis. Maybe you could have come up with another analysis which did not require the distance of the initial iterate from x star. Okay, all we are saying is, well, given this analysis says if your initial iterate is very far from x star, then the number of iterations will be those many more, I mean, almost squared, right? So we don't need the f of x star. We don't need it. I mean, there is an existential R based on what that f of x star is. And if we are too far, then there will be a quadratic growth in the number of iterations proportional to the distance. Is that clear? So we don't need the value of x star, sorry, f of x star. We are doing it in an existential manner. Is that okay?
So sir, we can't use this inequality, this bound for deciding the number of epochs we need, because anyway we don't have R.
Yeah, but all we are saying is if my initial iterate is fixed, right? If and I try different epsilons, I give you an epsilon 1, epsilon 1, epsilon 2, epsilon 3. then I can come up with an estimate of how my number of iterations will grow. Right. So all this is modulo that we have the same initial iterate. So let me write this. So above analysis, yeah, let me write this separately. The analysis below assumes that we are always dealing with the same initial iterate x1, right? We are not changing it, which determines r. And all we are saying is how does the rate grow given this assumption? Is that okay?
Yes, sir.
We are giving a recipe for the number of iterates under this assumption. The recipe for number of iterates under this assumption is that if you want to get more close to the optimal, you would need, right, number of iterations inversely proportional to the square of how close you need to get to the optimal. In some sense, that's why we are using the big omega notation. Big omega notation is because we don't want to be bogged down by the fact that there's an R and a B. I mean, you can ask the same question about B. Of course, I mean, R is slightly more tricky because it's initial iterate for the same function, but B is fixed for that function. But again, if the tighter the B, the smaller the value of B, you can get the pure number of iterations, right? So we are trying modulo all that. We have this inverse quadratic growth, right? As you want smaller and smaller gaps, you need to have those many more quadratic growth in equations. Is that fine?
Yes, sir.
Now, yeah, we saw some advantages. But there are disadvantages. There are more disadvantages than advantages for this. It's a very naive algorithm. We are not very happy. Naive analysis, rather. Algorithm is also somewhat naive, but analysis is certainly naive. It's slow convergence. To achieve an error of 0.01, what happens, right? We require 10 raised to 4 r square b square iterations. But if you wanted an error of 0.001, like now you suddenly need 10 raised to 8 iterations, which is like too much. So this is a problem. I mean, I've listed some disadvantages, but there are actually more disadvantages. Let me list some more. Okay. Is this disadvantage clear to everyone? I mean, I've been hinting at it already in the previous slides, but now we have got a lot more explicit about it. Any other comments? So let me look at other disadvantages. Okay, by the way, the disadvantage of the assumptions we have assumptions. They're like this analysis. It's specific to this analysis of the algorithm. So we are not going to change the algorithm right away. We'll try and see if we can get better analysis. So what are the other disadvantages? I mean, there's do you say that there's a kind of magical gamma that pops up somewhere? We did say that it holds. Maybe looking at the minimum value of gamma. That's a problem. Why should we why should we not assume that gamma is obtained in a more principled manner? Right? Does not assume that the step size gamma is obtained in a more principled when I say principled I mean search based manner, right? So can realistically, right? So realistically gamma can be obtained using a whole bunch of search techniques. Okay. So what are those search techniques? So there are using search techniques such as exact backtracking, right? Ray search, and then backtracking ray search under until conditions, especially backtracking ray search, right? So backtracking specifically, backtracking basically keeps tracking back, right? Search, we call it ray because we want gamma to be greater than 0. So ray search continues until conditions such as there are Arduino conditions, Goldstein conditions, etc. are satisfied. So towards this, I'm going to give you extra and optional slides. They're optional, but it'll be nice, right? To have a look at it. I'll talk about a bit more about it. But the other is what do you mean by convergence? I mean, so we have invoked the notion of convergence here. Need to also appreciate different kinds of convergence, right? So this we say this is a slow convergence. What is a slow convergence about? This is the convergence is a very weak form. See, we talked about this omega, right? Is omega the right thing to do? I mean, somebody rightly pointed out, right? So can we have a more, I mean, better, more comfortable convergence? So we, again, I would say see extra optional slides. I'm not going to go to, I'm going to just flash them right now. But say we have R convergence. I might bring it up later on. Let's see. Right now it's extra and optional. It's certainly for the midterms it is. But we'll see if there's a need. I'll pull it up again later on. So R convergence was Q convergence. Let's so we'll not use big omega, small omega, right? I mean big O. That was just so the entire discussion on omega. It's okay if you don't completely understand. But this is a very weak. This is not the analysis we'll be using. Okay. So that's why I'm not going to delve into it. Okay, so we won't use this analysis. So it's less relevant for us. Because what we want really to know quadratic, cubic, and whatever in a more principled manner. There's a notion of Q convergence, Q linear convergence, Q quadratic convergence, and so on. Okay, so we'll look at that. I'll be posting those slides separately, but before I move ahead, I'm just going to quickly flash those slides, and then we can come back to. So I'm just going to show these extra slides on convergence. Hope you can see. It's the notion of rates of convergence. Okay, linear, superlinear, sublinear. as an iterates. The same thing I showed earlier, right? You want the function value to decrease. Now, which of these is impressive? The superlinear convergence, sublinear, or linear? What impresses you most? Which is the best of the three? Hello? Can you see the screen?
Yes, sir.
So which is your highest priority here?
So it depends on the need.
Depends on the
Need, what we need.
I mean, we
Like,
want to converge fast, right?
no, like, sir, if we do not have much budget, like we have to do it in few epochs, then sublinear would be good. And if we have little more budget, superlinear would be better.
Right. But typically we'll assume that we have some number of epochs. I mean, we cannot be too miserly, right? So we have some amount. I understand, you know, you're talking about this part right here. Modulo this part, superlinear, right? But then subsequently it just goes down very fast, isn't it? A sublinear kind of really stagnates after a point. Yeah, I can think about it. I mean, would this be a preference? 1 followed by 2 followed by 3. Yeah, I'm leaving this as food for thought for you. Okay, so again, the notions of R and Q linearly convergence. So if you have a sequence Sk minus S star being less than equal to Vk, and then Vk converges Q linear to 0, then we call that S1 to Sk is R linearly convergent, where the notion of Q linear is that Vk plus 1 minus V star its ratio with respect to Vk minus V star is less than equal to R. If this is Q linearly convergence, R is like, okay, R is a little weaker thing. You're saying it has an upper bounded Q linearly convergent sequence, linear, and we are calling it Q. We'll be seeing this very soon. This is a quotient of the norms. So this quotient is making it is giving it the name Q. I made it optional so that I don't want to again make this sound like a full class on it. Otherwise we'll be just stuck. Okay, so Q linear convergence typically implies that you have R linear convergence, but R linear convergence doesn't imply the other way. So Q is an order of convergence. R is a rate of convergence. Okay, so I'm just talking about Q superlinear. So here superlinear convergence is when even if you take the square of the previous difference here, right, and take the ratio of the current difference to the square of the previous difference, that limit in a limiting sense goes to 0. And in the sublinear, Q sublinear, you're saying that it goes to 1. But you can have a general order P. Instead of the 2, you can have a order P. Okay, so yeah, again some examples also in these slides. Look, what is fast, what is slow. So both S1 and S2 converge to 5. Right? 5 plus 1 upon 2 raised to n, and the other one is 5 plus 1 upon 2 raised to 1 upon 2 raised to 2 raised to n minus 1. What would you expect to converge slowly? If you study S1, S star is 5 and Q convergence order P equals 1. Whereas for S2, you have P equals 2. Okay, now you need to think, which is better, P equals 1 or P equal 2? What's your intuition about S1 versus S2? What seems to converge faster? Anyone?
S2 looks faster.
S2 looks faster. Okay, so I maybe can give some thought to it. Others can also give their thought. So then looks like P is equals to higher is better. Okay. So that's Q converges of order P greater than 1 are super linear. That's what I was kind of canvassing for earlier. Okay, so this is meant to be optional reading. I mean optional from the exam point of view, but I would say from understanding the course, please do read. I mean I would encourage you to read. Just that I don't want to cover in the exam something I have not spent sufficient time teaching in the class, so therefore I'm calling it optional. Okay, and R convergence, this is key. What we have, I mean the convergence analysis for Lipschitz continuity has this R convergence. It's not even R actually, it's almost R. So it's even weaker. So that's how pathetic this convergence is. Right? It's almost R convergence. I mean it's not too bad, but at the same time, we just see the gradient descent with Lipschitz continuity as convergence rate 1 upon k. Right? So basically to get f of k minus f of star less than equal to epsilon, we need order 1 upon epsilon iterations. Okay. What I've also given in these extra slides is the general notion of descent algorithms. Let's see if I get time to cover, and then another thing I cover in great detail in the slides, in these optional slides, is finding the step size. So I talked about exact ray search and backtracking ray search. Okay, so exact ray search is finding the next t that oh, what happened? Finding the next t that minimizes the f with the current step size, current step direction, sorry, f of xk plus t times the current step direction, which could come from any other descent algorithm. So this should in general tell you that the next iterate will give a lower function value than the current function value. That's exact, but you in practice what you do is backtracking. You can't find the exact iterate of always. So you try and do some backtracking. So I talk a little bit about, I give details on how this implies a sufficient decrease. This is also called the RBO condition. It's called the RBO condition. Okay. So the algorithm is as follows: you choose a beta, then keep updating till you reach the sufficient decrease condition. There are a couple of important points here. The way you are going to iterate on the beta, and way you would use beta is like you're going to shrink your step size t with a multiple beta. Beta is less than 1, by the way. And you do this so that there's a sufficient decrease. That's the whole idea of backtracking lines. There's sufficient decrease. And we don't want to make minuscule, insignificant decreases. So I'll see if I get time later on. I'll talk about this a bit more. So, but I give examples here. And then there are strong wolf conditions, which are in conjunction with the RMO condition. They are even better. They will give guaranteed decrease and so on. Okay, so if your function has convexity, you can actually get strong wolf conditions. You can satisfy strong wolf conditions, right? And so on. So exact ray search does better than empirical ray search only sometimes, right? The exact choice of C1 and C2, they are not very important. The C1 and C2 which come from RMO and the wolf conditions. So then I give example of steepest descent algorithm, yeah, which is a more general framework for gradient descent. Okay, so I'm going to leave this as extra reading for you. I also give convergence of descent algorithms in general. And how the convergence can be analyzed, very generic. This is probably the most generic analysis of any descent algorithm, and the most generic use of backtracking research. Most generic analysis of the most generic descent algorithm, because gradient descent is an example of descent algorithm. Gradient descent is only a special case. But not only that, what we have done here is also analysis, not for some magical gamma, but analysis based on step size that's obtained right under the backtracking research. Okay, so yeah, in case you're interested, this might be helpful, but in practice, you don't need to go this far. You don't want to do it for generic descent algorithms, though the analysis based on step size using backtracking research is certainly interesting. Okay, so it's a bit involved, and that's another reason I'm not doing these proofs. I mean, this just takes will just take a lot of time. You have to bring in the C1, C2 constants and how they affect and so on. Okay. And I give a couple of other algorithms. So I'm going to stop this discussion here. Go back to the main part. This, as I said, is optional. I think yeah, the rest of this is just convergence of the gradient descent, a special case, right? Here, what I do is again the gradient descent algorithm specifically, but under the backtracking research. Okay, I've used Lipschitz continuity and all that. I mean, you might find this interesting because now it's more specifically gradient descent, but under better step size. Okay, here backtracking search. We have made use of the backtracking search algorithm here. With backtracking step size, search. Okay, so this kind of more general than our class proof, where we use some magical gamma, minimizing gamma. So like this, but more involved, right? So you'll have to do a little bit more work and so on. Yeah, this is just running you through what and how backtracking research weaves together with Lipschitz continuity. Yeah, okay. So this I'm going to just leave it at this. Going back, what I'm going to now leave you with a homework problem, which I think is going to be important. Back to these slides. Yeah, we go to this slide. This is very important. So we are not very happy about what we got using Lipschitz continuity, right? Can we do better? What does better mean, right? And that's why we took the detour to give you an idea of optional reading material, where rates and orders of convergence are used. I talked about Q, linear, quadratic. Q is basically right the order, and then there's a R, which is the rate of convergence. Right. We give an idea of Q linear, versus Q sublinear, linear versus R convergence. This is a very weak form of convergence, right? So no, that can help you better appreciate what is better. Right, more rigorously. Our current intuition is exactly as follows. We say that if I have, so we are trying to use a little bit of intuition for motivating here. We are saying that if it's going to take to error of 1 by 100 is going to take 1 by 10,000 times. I mean 10,000 more epochs. That's our problem, right? So our running intuition for an error decrease by a factor of 0.01, we needed basically 10,000 times more epochs, iterations. That is unacceptable. That's our main concern. Okay, so instead of resorting necessarily to all that convergence rate, we are trying to give a little bit more intuitive understanding. If the class feels I want more rigorous understanding, certainly we can do that. But let's just stick to this. And then our question is, can Lipschitz smoothness help reduce that? Okay, and we know that Lipschitz smoothness put a bound, right, upper bound on how fast the function changes. The curvature. Lipschitz convexity says, well, there's at least so much rate of change. That's what we are trying to motivate to this image. So the question is, can Lipschitz continuity bring us down, or Lipschitz smoothness? So can say T, which was kind of, if you look at the previous slides, we were saying that T is greater than or equal to 1 upon epsilon square, right? And I know R and B are of concern to us. So greater than R square, B square, by epsilon square become. Now what? Now can we get something like greater than or equal to 1 upon something, or RB, whatever, but some expressions, but you have 1 upon log epsilon. Okay. So alpha times 1 upon log epsilon. That would be interesting for us from a convergence perspective. So more of this in the next class, but I want you to, this is a homework problem for you. How can we use this Lipschitz continuity? This was Lipschitz continuity, Lipschitz smoothness, right? And can you use this Lipschitz smoothness property to go from 1 upon epsilon square to 1 upon log epsilon? That's a homework. Any questions? So this is my homework problem using Lipschitz smoothness. What can we do this? Okay, if there are no questions, then we'll conclude for today. Thanks. We'll see you on Thursday. You were able to hear me, right? Hopefully there was no
Yes.
network issue here. Thanks.